I want to tell you why zeta function is zeta function. So the story starts with Euler and continues with Riemann quite a bit later. And even though Euler was the person who wrote the relation first, Riemann gets the credit because he got most out of this relation. So what the Euler noticed was the following thing. Lots of people try to do this, understand the series. So he tried to understand what happens when you add lots of integers. And simplest thing you could do is you could take integer 1 to infinity. If you just look at the sum, this is not going to be good. This is going to diverge. So you say, well, let's say I look at inverses of 1 over n. Well, it turns out that's also divergent if you're careful. But if you look at 1 over n squared, that's a convergence sequence. So that's what Euler was trying to figure out. And he figured out that, if he put n to the power of minus s, then depending what this exponent was, sequence would have different values. And he gave this thing a name, and being educated in Greek things, he called it zeta, parameterized by s, and that's what the zeta function is, where n is a natural number. But then he realized he wasn't actually interested in this. What he was really interested in also, Riemann, was to count how many prime numbers are, because, there's a prime factorization theorem. It says that I can take any natural number n, and I can uniquely write it as a product of primes, some finite number of primes, to powers, L1, L2, L3. And as you know, this is true for any number. So for example, 6 can be written as 2 times 3, or, maybe 1 times 2 times 3. But 9 can be written as 3 cubed and so on. So every number has unique factorization. And then he observed that if I write following thing in terms of primes, so I write prime, and I write 1 over minus prime number, so prime, and I raise it to the minus s, what I can do, it's, simple, nothing. Each one of them can be written as a geometric sequence, so you can write 1 minus p to the minus s is a sum of, k goes from 0 to infinity, p to the minus s times k, so you can raise it to all the powers, they're just geometric series. And if you do this for all the primes, you'll produce all the natural numbers. So that's a Riemann zeta function. And it's an incredibly fruitful thing. There is something called Riemann Conjecture, which is irrelevant for us, but it's begotten most of the modern mathematics. It's really smart. Huge part of mathematics that we think about today was cooked up by trying to understand what happens when S is a complex number and look at what this function does in a complex plane. Now, we don't need this, but this is now the motivation for everything else that's called zeta function. So here it's totally straightforward. It's consequence of unique prime factorization theorem. But there are lots of other things that are prime in the following sense. You can think of this thing as a building block from which you construct, buildings or something. In particular, in dynamical systems, but there are thousands of zeta functions. well, maybe not thousands, but definitely tens and maybe hundreds. You ask yourself, is it true that, if I have some piece, for example, there's a trajectory that does this, could I use this trajectory to glue its copy to the end? It's very natural when you have numbers to multiply them and get other numbers. But the idea of all zeta function is that you think of prime numbers as building blocks from which you construct all numbers. So you have other situation in mathematics in which you have some objects which you can use as little building blocks, and from them you can build, let's say, buildings. In particular, in dynamical systems, you can ask yourself the following question. Suppose I start someplace and I use my law of motion to trace out a trajectory that dynamical systems like to do. And I get a finite segment, and I ask myself the following question. Is it possible now to restart at the end of the segment and trace out the same shape, same building block, maybe turned around and translated, but the same shape? What if I can repeat this maybe 3 times? And is it possible to build a longer trajectory of period 9 from 2 trajectories who have ran only 3 units of time? Just like I take prime number 3 and raise it to the power 3 and I get 9. The same thing. So that's a motivation for dynamical systems, zeta functions. And the idea is to use the right-hand side of this formula and ask yourself, can I construct a dynamical zeta function? So this general question of, can I build a bigger examples of dynamics from some basic building block, is what motivates dynamical zeta functions. And the idea is to write a zeta function that depends on something. There's some parameter here. In our case, it's going to be called, D, let's say. And now write exactly the same object that we had before over all possible prime pieces. So all little pieces of trajectories which you can use to build bigger trajectories, if that's what's true. And that's supposed to produce all trajectories. And now the difficult thing to understand, and we keep getting confused, but that's what we're doing when we're doing symmetry addictions. What you want this to be is this, you want to be the smallest possible bricks. So, this is a good brick. But from it, you can build trivially 2 bricks. This is a prime brick. And this is something that's a building, So the crucial notion in all this dynamical system is to figure out what's prime. And by prime, we mean something that's small, so small that I cannot take a piece of it. I cannot cut it up in a smaller piece and glue to it. So it's the smallest possible brick. And that's what kind of intuitively is prime. That's first thing you want to know about prime. Second thing we want to know about prime, it's a more mathematical statement. You want to define equivalence class. And that means that in my picture here, I could have taken this, or I could have taken, now I'll have them unglued. I could have taken this, or I could have taken the other guy. And each one of these things can be called prime. So there's a class of objects that are the same kind of brick. They belong to equivalence classes, and they're connected by an operation which is called a symmetry, which says, I know they're equivalent because there is a change of coordinate or some such operation that says I can take this hook and turn it around and move it and put it on the top of the other one. If they coincide, it's the same object. So I want to count it only once. So that means I want to have equivalence class. So what it means in terms of lattices that we're studying, when you have a lattice state, which is 7 lattice sites long and it has some shape on it, because this lattice state repeats itself periodically on entire lattice, starting point can be any of the 7 starting points. So we have 7 different looking objects, which are the same object physically, they're in equivalence class. So now what's brilliant about zeta function is about, instead of counting everything that can happen, which is, what this thing says, these are all possible natural number or all possible trajectories or all possible objects of some kind. We only count equivalence classes, or what we call in dynamical system orbits. So we take an orbit and we count it only once, even though there are lots of copies of it due to symmetries. So that's what we are doing. In particular, when we wrote this Bernoulli map, we thought there were 6 different pieces of it if slope was 6. But it's not true. There was a symmetry, and it turns out that halves of those pieces can be used to build it up. What we used to think was a prime object, it's not. It's actually constructed from other bricks. And that's a tricky thing we are doing right now. We're trying to find the smallest possible object, put it together, and that's going to give us the dynamical zeta functions. Those dynamical zeta functions are the most economical ways of summarizing all information you know about a system by saying these are all possible smallest objects you can build it from. And if you need to build a building, well, in this case, the operation is I use just geometric series to enumerate all possible things. They're written here. And if you have to enumerate all possible different looking states, we do a similar thing, which we take some derivatives, etc., and we get the generating function that counts all possible guys. But that one is stupid because that one overcounts. It counts, every time I have a lattice state of length 7, it counts it 7 times, even though physically there is only one that's just being moved around. Or if I have a cat whose head and tail are the same, it counts it as 2 cats because, I can flip it and head can become a tail. But realizing that I can't distinguish the two, I just cut the cat in half and then I find, it's a cat that has a tail and a waist or whatever, but it cannot be sliced in a smaller cat and reconstructed. So that's what zeta functions are. They're the most intelligent, most compact way of summarizing all things that are possible in given mathematical setup. Could it be number theory, could be dynamics, could be many other things. And what it does is it counts physically distinct things only once, and it doesn't overcount repeats of the things, it knows what's prime. That's why we need zeta functions.